Hello, we are Team 3. This is our final presentation, and we want to talk about aerial-ground collaborative teleoperation. Here's our content list. The paper we selected is Aerial-Ground Collaborative Sensing, Third-Person View for Teleoperation. Disaster place is dangerous to humans who conduct rescue missions. Nowadays, many robot system is used. Because of complex environment, it is hard to control autonomously, and it is better to use human decision and intuition. So teleoperation robot is essential. In SAR mission, it is known that exocentric view can drastically increase teleoperation performance rather than egocentric view teleoperation, because we can see all four-way vision around our robot. In this paper, they use micro-aerial vehicle to provide exocentric view, and the micro-aerial vehicle follows the unmanned ground vehicle. What we control is UGV, and MAV follows the UGV automatically using visual surveying. GPS is restricted if it is in severe SAR mission, so MAV follows UGV by AR marker, not receiving UGV's position data or GPS data. In this paper, they use model predictive control and roll-over control to moving MAV automatically. I will talk about detailed control scheme later. This paper talks about in the GPS denied environment, it is sufficient to configure the system with visual surveying use AR marker and just about rotational error, translational error, and so on. But there is no result about viewpoint. Actually, there are optimal viewpoints for each situation. For example, when passing the tunnel, exocentric like top view is insufficient. Egocentric like front view is suitable. But it is better to use exocentric top view when there are many obstacles. Therefore, we construct a system which is not fixed viewpoint, and user can easily change viewpoint during teleoperation, not changing MAV position. And we evaluate the performance of our system by comparing it with existing system in SAR mission scenarios. Before getting started, we find another paper about comparing each viewpoint in SAR teleoperation mission. They compare three types of view: front camera view, pole camera view, and flying camera view. In case of number of search victims, front camera view is worst. And the number of collisions when moving, front camera is also worst. The other features are shown in the table, but all cases it still provide fixed view. To replicate our paper, we use ROS and Gazebo. We select a mobile robot called Husky as UGV and drone called Fireflies as MAV. And we attached AR marker on the top of the UGV. We use various sensor, camera, and LiDAR. We control the UGV by giving the velocity command human input through the wireless controller. This is whole system control flow, including how MAV can track UGV. First, human control the UGV. The camera on MAV, and by tracking algorithm, we can know position and orientation difference between them. Important thing is we have to set reference frame to control MAV. And then reference frame to MAV, desired position and orientation metrics set as the desired pose. After desired pose is set, the MAV generates a trajectory, and the nonlinear model predictive controller is used for drone to generate the proper trajectory. Driving the drone is actually low-level control like PID and so on. This is the final motion of MAV. Visual surveying acts in this way, and we can get feedback about moving MAV's view.
So this is the result of our replication and implementation. So as you see, UAV can follow UGV very well, but there's some oscillation because of control. It's not perfectly optimized. So results show that teleoperator can have more wide view because of UAV field of view. Also, due to this advantage, search and rescue mission could be more informative and efficient. But because of UAV behavior, UAV cannot follow when UGV is under desk or AR marker denied area. Also, UAV's vibration or shaking from disturbance cause large visual movement, which teleoperator make hard to control UGV and lower the teleoperation transparency. Also, it can cause embarrassment and motion sickness. Because of this limitation, we suggest new method, personalized exocentric view. So, with only top view from UAV, it is hard to get surrounded terrain height. Also, because of disturbance like wind, UAV suffer from vibration and rotation. This phenomena derive unstable behavior as visual feedback. So, teleoperator can be hard to control UGV and also lose transparency at teleoperation system. So we suggest new approach for defining exocentric view, which is generated from reconstructed scene. RGBT sensor from UAV can generate 3D reconstruction map, and we can apply personalized view which teleoperator can manipulate UGV comfortable. RGBT sensor can map limited area under desk or tunnel. Also, teleoperator can search around obstacle which disturb the UGV moving to SAR object. For short-term mapping, we use 3D point cloud scan match algorithm called NDT, Normal Distribution Transform. NDT make voxel grid and calculate the mean and normal distribution using point cloud at each cell. Using score function P, we can find parameter which can align normal distribution between two point cloud. Optimization process is conducted under Gauss-Newton algorithm with Hessian matrix. Using NDT-based matching algorithm, we can get position and matched point cloud. Also, we use point cloud from the UGV, which is adapted with LiDAR scanner. We use short-term mapping for real-time performance. Also, most of search and rescue mission is consist with diverse environment that change every moment. So we use short-term SLAM, which use only submap keyframe, not global map and optimization. Based on short-term mapping, we can reconstruct the scene. Based on this scene, we can generate multiple viewpoints, which is comfortable for teleoperator. Also, using mapping algorithm, we can generate static map which map frame is fixed with base length of UGV. Finally, we can get scene which is not vibrate or shaking. This can derive less motion sickness and getting more information about surrounded obstacle around UGV. Left picture is short-term NDT SLAM result and right video is result of our suggested method, personalized exocentric view generation. We use ST NDT SLAM and simply accumulate depth information from UAV to base length of UGV. LiDAR mapping has less noise because we use SLAM algorithm, but simple accumulated RGBD information from UAV has noise came from unstable behavior and disturbance of UAV. So we conduct experiment under method. We assume the situation which construction site is demolished. Using UGV and UAV, we need to search and rescue people in demolished site. First is experimental conduct simulation at 6 people area, which designed for familiar to demolished environment. Teleoperator can train and get familiar with UAV UGV control system. Time is limited in 3 minutes, and then experimenter conduct SAR mission at right blue side. Teleoperator need to search and rescue 7 people with harder environment like narrow path or hard to drive train. Yellow point is people who need to rescue. Rescue target is randomly generated at certain coordinate. Experiment conduct with 5 teleoperator. 5 teleoperator performance evaluation is conducted under criteria expressed in this page. Number of collision, completion time, and Likert scale. Likert scale is tool for estimate teleoperators performance and mind. Likert scale consists with comfort, motion sickness, hardness of mission, and adaptation of teleoperation system. Experiment is conducted with 3 viewpoints. First is front egocentric view, second is top exocentric view, and final is suggested personalized exocentric view. This experiment set up an teleoperation system of each viewpoint generating using UAV and UGV. Front view has narrow depth, high transparency for teleoperation. Top view has high information and motion sickness. but our method catch all the benefits from top view and front view.
I will show you the results of the experiments and discuss and analyze about the results. The plot above shows the number of collisions while conducting search and rescue mission. The egocentric view, which shows the video from the camera attached to the MAV, has the largest number of collisions, and our suggested views had the smallest number of collisions. In case of the completion time, the top view, which shows the video from the camera attached to the drone, shows the most completion time, about 50 seconds more than others. In fact, this result is different from what we talked about in the related work part. This is because our experimental environment is much more complex than that in related work. Plus, there are many obstacles that prevent the MAV from recognizing UGV. There are 5 questions for evaluating our system usability using Likert scale. First question is, I felt comfortable driving the vehicle. The results show that MAV view is the most comfortable view for the teleoperator since people are familiar with it. Second question is, it was easy to identify where the robot is. The results show that our system is the easiest way to localize the robot. Third question is, it was easy to find all the victims. The results show that our system is also suitable for search and rescue mission. Fourth question is, I could easily get used to the mission. The results show that MAV view requires much less effort to get used to its configuration. Final question is, I couldn't feel motion sickness. Actually, motion sickness is quite important for teleoperation task. Surprisingly, the results show that our system is better than MAV view, which people are familiar with. In conclusion, our system showed much smaller number of collisions and less completion time. Moreover, our suggested system got high score on Likert scales, especially for these 3 questions. However, there exist the limitations. First, since all people got used to first-person view, our system couldn't beat the comfort and familiarity that first-person view gives us. Second, for our experimental setup, participants could control UGV with one hand, while using the other hand for changing viewpoints. However, for the case when teleoperator need both hands to control UGV, it may cause additional time to adjust viewpoint. At last, let's talk about future works. For now, MAV itself cannot avoid collisions. But self-collision avoidance is required for search and rescue mission in real world. Moreover, fusing ground and aerial sensors would be beneficial for localizing the robot's position. Furthermore, simulating multi-UGV and MAV system would be beneficial for large-scale search and rescue mission in real world.